Hello guys, so today in this particular video we are going to see the numerical based on vapor compression refrigeration. So this is the first numerical. This numerical was asked in December 2023 examination, question 3B for I think 12 marks or something. So this particular 12 or 10 marks. So this particular numerical we will just note down the given data first of all, and then we will solve the problem. Okay, so we'll read the problem over here. So a simple NH3 vapor compression cycle has a compressor with a piston displacement of 3 cubic meter per minute is given, and having the condenser pressure of 12 bar, evaporator pressure of 2.5 bar. This liquid is subcooled to 20 degrees Celsius by soldering the liquid line to the suction line. So subcooling is given. The temperature of vapor leaving the compressor is 100 degrees centigrade. Okay. And the heat rejected to the compressor cooling water is 6000 kJ per hour. Volumetric efficiency of compressor is 0.8. We are supposed to find out the capacity of the system, indicated power, and the COP of the system. Okay, so one by one we'll just go for this particular problem. Okay, I'll just note down first the given data over here. Given data, we'll first note down the refrigerant over here. Refrigerant is the NH3, that is ammonia. Then they have given the piston displacement. I am writing the short form piston displacement as 3 meter cube per minute. Then they have given the condenser pressure and the evaporator pressure. So that pressure I am showing on the pH chart, so that will be better for you to understand the things. So this is the generalized pH chart I am drawing. So there are two pressure lines, one is the evaporator pressure and another one is the condenser pressure line. So the lower will be the evaporator pressure, which is nothing but the 2.5 bar, and the upper one is nothing but the 12 bar, which is nothing but the condenser pressure. And the liquid is subcooled to 20 degrees Celsius by soldering the liquid line to the suction line. Okay, and the temperature of air leaving the compressor is 100 degrees centigrade. Fine. Okay, so that is what the data given over here. Now what we are supposed to do over here, that we should get the values of the enthalpy by using the pH chart. Okay, as they have given the simple vapor compression cycle, it means that the inlet to the compressor is dry and saturated. So here I will have the inlet to the compressor point, that is nothing but the point number 1 will be over here. From this particular point up to 12 bar pressure line and up to the temperature of 100 degrees centigrade, there will be the compression. Okay, so this particular point will be the point number 2. Then there will be the condensation over here. So while having the condensation, they have given that the liquid is getting subcooled by 20 degree. So somewhere over here I will be having the point number 3, because there is the subcooling. Ideally the point 3 will be over here on the saturation curve in simple VCR system. However, they have mentioned about the subcooling, so the point number 3 will be shifted over here in the liquid region, and then 3 to 4 there will be the constant enthalpy expansion process will take, and from 4 to 1 it is nothing but the evaporation process, where the heat is getting absorbed from the area to be cooled. Okay, so 1 to 2 is the compression, 2 to 3 is condensation, 3 to 4 is nothing but the expansion process, and 4 to 1 is nothing but the evaporation or the heat absorption process. Okay, now this is also known as the refrigerating effect produced process. Okay, so what we are supposed to find out, that is the capacity of the system. So the capacity of system is nothing but the cooling capacity. Basically it is nothing but the cooling capacity, which is also known to be the refrigerating effect, and this value we are going to find out in terms of refrigeration. We will find this answer in terms of refrigeration. Then we are supposed to find out the indicated power and the COP of system. Fine. So what we will do, we will first plot all the points on the pH chart, and then we will go about this particular data which is to be found out. So first what I am doing, I will just write down the formula for each of the thing. So for cooling capacity, the first one is the cooling capacity, that is nothing but the heat absorbed, and that formula will be nothing but the difference of enthalpy across the cooling process. So if you see over here in the pH chart, the cooling process or the heat absorption process is from 4 to 1. Okay, so the enthalpy difference across this particular process is H1 minus H4. However, the answer of this particular will be in kilojoule per kg. That answer will be in kilojoule per kg. Okay, so I need to convert this particular kilojoule per kg to tons of refrigeration. Obviously, I need to multiply this particular term by mass of refrigerant. Then and then only I will just, let's say I am putting the mass in kg per minute, okay, into kilojoule per kg. So kg get cancelled. Finally, I will get the cooling capacity in kilojoule per minute. Now this kilojoule per minute I can easily convert it to TN. Okay, so that detail we will see when we put the values over here. Then in the second one, that is the indicated power. Now indicated power, the formula for this is nothing but the mass of refrigerant into the enthalpy difference across the compressor. So enthalpy difference across the compressor is H2 minus H1 divided by the efficiency of this particular compressor. Efficiency of compressor. This is the formula for finding out the indicated power. And the third one, that is nothing but the COP of system. COP is nothing but the heat absorbed divided by the work done. Now in this case, the heat absorbed nothing but the cooling process, which is from H1, H4 to H1. So enthalpy difference across this particular cooling process is H1 minus H4, and the work done is nothing but the work done by the compressor, which is H2 minus H1. Okay, so these are the three basic formula, and by using these formulas, we can find out the required things. Fine. So for this particular problem, obviously I need to have the pH chart. Okay, I'll go to the pH chart. Yeah, so this is the pH chart for ammonia. You can see over here, this is the R717, which is nothing but the ammonia. Okay, so as by the given data, we will just note down the, we'll plot the points over here. The one thing we need to understand over here, that is the pressure which is given over here in this pH chart is in MPa. It is in the megapascal. However, the pressures which are given to us are in bar. Okay, these are in the bar. So condenser pressure which is given over here is 12 bar. It is in 12 bar, and whereas the evaporator pressure is given as 2.5 bar. Okay, we will just confirm once. Yes, 12 bar and 2.5 bar. Okay, so we need to convert this 12 bar and 2.5 bar first into MPa, and the conversion is very easy. That MPa is equal to bar value divided by 10, as simple as that. Okay, so the condenser pressure here, it is given as 12 bar, so it will become, now this condenser pressure will become 12 by 10, which is nothing but the 1.2 MPa. It will be 1.2 MPa, and the evaporator pressure will be 2.5 divided by 10, which is nothing but the 0.25. Which is nothing but the 0.25. So this is how we will have the values over here. Now what I will be doing, I will be just plotting these two pressure lines over here on the pH chart, and then we will go about the problem. So first I will go for the 0.25 line. So this is 0.2. So here we will be having the 0.3. Somewhere over here we will have the 0.25 line. Okay, centrally. So let's say I am getting the 0.25 line over here something. Okay, so as we have seen already, the compressor inlet is the dry and saturated. So this is the evaporator pressure. Let us draw this particular line. Okay, fine. And then 1.2 bar. So 1, 2, this is 1.5. Somewhere over here you'll have 1.2 bar pressure line. Okay. This is 1.2 bar. Oh, sorry, this is 12 bar. 12 bar, that is nothing but 1.2 MPa, and this is 2.5 bar. Okay, now what is given? It's a simple VCR system. So the point number 1, that is the inlet to the compressor, will be dry saturated vapor. So the point number will be the intersection of saturated vapor line along with the evaporator pressure line. So I'll be having the point number 1 over here. This is my point number 1. This will be the point number 1. Now from point number 1 to 2 there is the compression process. However, the compression will be up to the 12 bar pressure line. In this particular case, generally what we do, we are following the constant entropy lines over here. But in this problem, they have given the temperature. They have given the temperature at the exit of compressor, and the temperature is 100 degrees Celsius. Now if you see here, that is this particular value, that is 100. So this is nothing but the temperature line. On the pH chart, you know that the temperature lines will follow vertically downward over here, something like this. Then horizontal, perfectly horizontal within the saturation curve, and then you'll have the curve over here. Okay, so let's see, this is the 100 degrees Celsius. So wherever this 100 degrees Celsius and 12 bar pressure line, wherever they are intersecting to each other, mark the point number 2, that is the exit of compressor, because compressor exit is 12 bar and 100 degrees centigrade. And then you follow this particular line over here. Okay, you follow this particular line. Fine. So this is the, just a minute, I will just erase those things, make it proper. Okay, so 1 to 2 is nothing but the, what I can say, the compression. Right. Then 2 to 3, ideally the point 3 will be on the saturation liquid line. However, they are saying there is a the subcooling up to 20 degrees Celsius. Now if you see just over here, this is the 20 degrees Celsius line. This is 0 degrees Celsius minus 20 degrees Celsius. So this 20 degrees Celsius will be the vertical line over here, just out of the curve over here. This is the vertical line, then horizontal, and then curve. Okay, that is the temperature line, how it follows. So up to 20 degrees Celsius the subcooling is done. So I'll just extend this particular line up to 20 degrees Celsius, and wherever it is intersecting this particular 12 bar pressure line to the 20 degrees Celsius, I will mark this point number 3. Now you know that the condensation process will be at the 12 bar, will be at the higher pressure. Okay, and in the condensation there is a subcooling is taking place. Okay, and hence we have shown the point number 3 over here on the condenser pressure line and up to the 20 degrees Celsius line. Then from 3 to 4 it's a constant enthalpy line over here, which is the perfectly vertical line, and wherever it is intersecting to the evaporator pressure line, I will get the point number 4 over here. So this is the evaporator process. 4 to 1, 1 to 2 is the compression, 2 to 3 is the condensation, and 3 to 4 is the what you can say, the expansion process. Fine. Now at the various points like point number 1, 2, 3, 4, I will note down the enthalpies. These enthalpies are required to calculate the required data. As you can see, all the values or the formulas are in terms of the enthalpy. Fine. So we'll just go on noting down the enthalpy values. So with respect to point number 1, if I draw a perfectly vertical line over here, somewhere it will be falling between 1400 and 1600. So this is 1400 line, then we'll have somewhere over here 1500, here 1450. So this will be something around 1420, 1430. Okay, so perfectly when you mark a line with a scale, you will get that perfect value. Now for this particular moment, assume that this value is around 1420. Fine. So we'll mark the line over here, rather I will mark the enthalpy. So assume that, okay, I'm writing it over here. Enthalpy at point 1 is 1420 kilojoule per kg. Okay. Then with respect to point number 2, okay, it is 1700, somewhere around 1680. Okay, it is around 1680. Fine. So H2 will be 1680 kilojoule per kg, and then H3, this is the perfect vertical line up to this, so around 300, 280. Okay, so this H3, now this H3 and H4 are equal because 3 to 4 is the isenthalpic process. So H3 is equal to H4 is equal to, the value is around 280. Fine, 280 kilojoule per kg. Okay, so these are what the enthalpy we have got. Now one by one we can get the data. So first one, we'll see what is they have asked. Yes, they have asked the cooling capacity. Okay, fine. So cooling capacity, the formula is mr into h1 minus h4. mr into h1 minus h4. Fine. So in this particular formula, I know the value of h1, I know the value of h4, but I don't know the value of mr, that is the mass flow rate of refrigerant. And to get this mass flow rate of refrigerant, I can make use of the data given over here, that is the piston displacement. So piston displacement is given as 3 meter cube per minute. So this data I can make use to find out the mass. Now the formula for piston displacement is mr into V1 divided by volumetric efficiency. Okay, this is the formula to get the piston displacement. Now this V1 is nothing but the what you can say, it's a specific volume, mr, mass flow rate of refrigerant, and this is the volumetric efficiency. Now this particular value of a V1 specific volume, we can get it from the chart with respect to the point number 1, which is the inlet of the compressor. Fine. So what I will do over here, we'll go. Now we can see that here actually directly specific volume lines are not given, but they have given the density. So density is 1000. Here it is given as 100 kg per meter cube. Okay, and the specific volume is the reciprocal of density. Fine, reciprocal of density. So you can see these dotted lines are nothing but the density lines. These are the dotted lines which are nothing but the density line. So with respect to the point number 1, if you observe the dotted line, this dotted line is nothing but will have the density of 2. The density will be equal to 2 over here. Okay, this is the dotted line which we are supposed to follow with respect to point number 1. Okay, so the density is 2. Okay, so I will get the row 1, you can say it is nothing but the 2. Therefore, the specific volume V1 is equal to, this is in kg per meter cube. Okay, so V1 will be 1 by 2, which is nothing but the meter cube per kg. Okay, so V1 will be 1 by 2. This value we have got. Now we'll just see what about the unit. Now the piston displacement unit is given in meter cube per minute, which is equal to, the efficiency is unitless. Okay, so mr, obviously the mass will be in kg, divided by, I don't know, as of now I will just keep it as it is, into the specific volume unit is meter cube per kg. Okay, so this kg will get cancelled over here, correct now, and I will get at the denominator here it is the minute. I want to have the meter cube per minute over here, so obviously this particular mass will be in kg per minute. So whatever answer you are getting for the mass, that answer will be kg per minute mass. Okay, that will be the kg per minute. So by putting these particular values over here, let's say piston displacement 3 is equal to mr into 1 by 2 divided by the volumetric efficiency. From this you can get what the value of mr is. Okay, you can get the value of mr. So you can easily calculate the mr value. Then this particular value in kg per minute, this is in kg per minute. Fine. So from this, once you get the mr, you can easily find out the cooling capacity. Which is equal to mr into h1 minus h4. So mr you have already calculated, h1 h4 you know. However, the unit of this, because mr will be in kg per minute into the enthalpy will be in kilojoule per kg. So kg get cancelled, will finally remain with the kilojoule per minute. Okay, So convert this kilojoule per minute to tons of refrigeration, because I want to have the cooling capacity in tons of refrigeration. So we know that the relation that 1 TR is equal to 210 kilojoule per minute. So whatever answer you are getting down over here, just divide that answer by 210 to get the cooling capacity in tons of refrigeration. Okay, so that is the first bit you have solved. Second bit, that is the, what you can say, the indicated power, okay, IP, that is nothing but MR into H2 minus H1 divided by the efficiency. So this will be value, obviously you know MR, you have calculated, H2 value you know, H1 value you know, and the efficiency you can use this 0.8, okay, 80% efficiency, you can get the indicated power over here. Now again, this indicated power, if you are putting this particular MR in kg per minute, you will get the indicated power in kilojoule per minute. Convert that kilojoule per minute to kilowatt, because generally the power are represented into the kilowatt. So divide the entire answer by 60, whatever answer you are getting divided by 60, you get the indicated power in kilowatt. And then third, that is nothing but the COP, which is very simple, that is H1 minus H4 divided by H2 minus H1. So H1 you know, H4 you know, H2 you know, okay, so that is nothing but something around, we'll have the COP H1 minus H4 is 1420 minus 280 divided by 1680 minus 1420. Okay, whatever answer you get, that is nothing but the COP, and the COP is unitless. So this is how you're supposed to solve the problem based on the VCR. So this problem was asked for 2 times in our 2019 syllabus revision. Okay, so you can prepare this particular problem. I'm leaving the calculation part up to you. You just do the calculation and put the values. Okay, thank you guys.